segment 3 of chapter 4. We're going to pick up with acids and bases. That's where we left off. So we just finished talking about ionic solutions and net ionic solutions. And so common laboratory reagents are acids and bases. We've already worked with one concentrated acid thus far, which was the sulfuric acid in our aspirin lab. Acids typically would be tart and have a sour taste. So if you would have taken that sulfuric acid and diluted it first and then put it in your mouth, it would have a sour taste. Don't do that. If you haven't done the lab yet, don't put any concentrated acids in your mouth, please, especially in lab. For bases usually taste bitter and have a slippery feel to them. So soap is a common base. So that should hopefully give you an idea. Saponification is making soap. So caution, never taste, feel, or smell laboratory chemicals. You'll just have to take our word for it there. And maybe, as I gave you some ideas here, that soaps are typically basic. They'll be pH balanced. We'll learn what that means here in a bit. We're going to be focusing on what's called an Arrhenius acid. So there's a couple different different definitions for acids. There's the Arrhenius acid, where the substance is going to react with water to produce what we call the hydronium ion. And you've heard that phrase a little earlier. And that's where we make H3O+. So H3O+ is referred to as the hydronium. And so conceptually what's happening here is if we take an acid like HCl, it's going to dissociate, which we just saw in segment 2, and it's going to mix with water. And when that happens, the water is going to accept the proton from the HCl. So now we have the Cl as a minus charge, and now we have H3O+. So the hydrogen from the HCl has actually now combined with the water to make this H3O+. And so the way we use the phrases here is we have acid plus water would give us the anion plus H3O+. And then the Arrhenius definition would be any substance that makes that guy is an acid. So for a general formula, we would say HA plus H2O produces A minus plus H3O+. Okay, so another example would be acetic acid. Now, if you remember, acetic acid is a weak acid. It's a weak electrolyte. And so here, it's still going to go through the Arrhenius equation idea. So the hydrogen that's with the acid is now going to go to the water to make H3O+, and we'll be left with an acetate anion. Now, ions form where none have been before in the ionization reaction. So substances that produce OH- is the Arrhenius base. And this is why we needed a separate definition for acids and bases, which would be the Bronsted-Lowry definitions. And so here, for the Arrhenius definition, it has to be a substance that forms OH- or O2-. So molecular substances. So ionic compound containing hydroxides. So like all your metal hydroxides would be bases. Okay, they're going to dissociate into the metal and the hydroxide ion. All right, you do need to memorize your strong acids. So this is your list. We have perchloric acid, chloric acid, hydrochloric acid, hydrobromic, hydroiodic, nitric, and sulfuric. Unfortunately, you definitely want to know, call them the power 5, which are these guys. Okay. So the HCl, the H2SO4, and the HNO3 are common strong acids in a lot of manufacturing processes. So you really want to know for sure those three with no doubt. And if you can remember the HCl, then the HBr and the HI are easy to remember because they make up the rest of period 7. Now notice, not period 7, group 7. Oh, I'm losing it tonight. Group 7. Now notice there's no HF. Okay, so hydrofluoric acid is not a strong acid, so that's not a typo. It's the only group 7A acid that's not a strong acid. Astenine is not really found, so you don't really see that one. So if you go all the way to the bottom of group 7A, we don't see that acid that often. Okay. Now, what does it mean to be a strong acid? Well, it's just like talking about electrolytes. That means they're going to be strong dissociations. So HBr, for instance, completely ionizes to make H3O+ and Br-, okay? Which means Again, good electrical conduction there because they're a strong electrolyte. Strong bases are bases that dissociate completely in water, so same idea, same topics. Soluble metal hydroxides like KOH then would be a strong base. It's going to completely dissociate, and they also will make good conductors because they're also strong electrolytes. Now, they will behave as aqueous ionic compounds. Okay, so even though they look like they might be molecular, these acids and bases, they are definitely going to be ionic. Now, common strong bases are all of group 1A. So lithium, sodium, potassium, rubidium, cesium, no exceptions. Your group 2A, also calcium, strontium, barium, all strong acids. Strong bases. Now, weak acids are any acid other than those 7 strong ones. So if it's not on the list, then you know that it's going to be weak. Okay? Which means they're also weak electrolytes. So that strong, weak electrolyte applies to acids and bases as well. Now here we also want to introduce you into organic acids. We've already seen one of them, and that's because it forms that acetate. That acetate is an organic component where it's just hydrocarbons with some oxygen in it. And so that's going to be organic acid. But there are other organic acids as well, like formic acid. Almost all of these will be weak acids. They're not completely soluble in water, especially the longer that carbon chain gets, it reduces the solubility. So why is acetic acid a weak acid? Well, that's because it doesn't completely dissociate, right? So we don't really want to write it this way. This is really not the way we want to write it, because this looks like it would be a complete reaction here, but it's actually not. So a lot of times what we like to do is give it a double arrow. So instead of that single arrow, we'll put in an equilibrium arrow saying that it goes to both sides. Now what happens is this reaction and this reaction are competing. So this reaction shows the CH3, the top reaction that is, shows the acid itself going to what we're going to call the conjugate base. Okay, this anion, if you will. In competition with that is that anion, now on the reactant side, going back to the acetic acid. So instead of writing in it with single arrows showing both reactions, again, what we'll do is we'll put in those double arrows. So instead of having a single arrow, we'll write double-headed arrows in. Now, if you are going to be taking the 151 course, you'll find that the size of these arrows will matter, but that's going to get into kinetics, reaction kinetics, which we don't talk about in 150. So if you're most engineering is 1 semester of chem and they're done, then you won't have to deal with kinetics. But if you are one of the other majors that need to take both semesters, then you'll get into the equilibrium constants here and the rates of reaction and going back and forth and for that competition. All right, so your turn. Which of the following is a weak acid? Okay, so which of the following is a weak acid? So again, you have to know your strong 7, and if it's not a member of the strong 7, then that's the weak one. So we know the acetic acid in this case is not a member of the strong 7. All right, which of the following is a strong acid? So now you got to pick out the one that is a member of the strong 7. One that always trips people up is phosphoric acid. They see that H3 and they just feel like it has to be a strong acid. One way to remember this is actually found in Coke. Okay, so Coca-Cola, Coke, phosphoric acid is in there. It's one of your ingredients, and it's why I usually consider Coca-Cola company to be some brilliant people there, because what they've done is they've taken phosphoric acid and they put it in a beverage that they tell you will quench your thirst, when in actuality phosphoric acid dries out your lips and makes you thirsty. So kudos to them for getting us addicted to Coke, Coca-Cola that is. So that is not your strong acid, because you're able to drink it, so you know it can't be too bad, right? And hopefully you'll remember that chloric, one of the odd ones, is your strong acid. All right, so this equilibrium that I was talking about, you have a dynamic equilibrium, which means we have 2 opposing reactions occurring at the same time. We refer to that as a chemical equilibrium. Now, we're not going to get into a whole lot of depth with chemical equilibrium because, as I said, this starts to get into kinetics, and kinetics is something you look at in the 2nd semester of general chem. So equilibrium, concentrations of substances present in solution do not change with time. So we're saying that once the equilibrium is established, the concentrations won't change. They'll be the same. Now, if it's a dynamic equilibrium, that means both reactions are occurring continuously. Right? So again, we'll represent those with a double arrow. So rather than having a single arrow pointing just to the products, we'll have a double-headed arrow. A forward reaction forms ions, where the reverse reaction is forming the molecules. All right, so Arrhenius bases, your molecular base, they will undergo ionization, right? Hydrolysis. So you'll take the base plus the water, and now water, instead of accepting the proton and making hydronium, will now donate the proton and form your base with an H plus on it and the OH minus. So our general equation here would be B plus H2O produces BH plus OH minus. And so now I can take something like ammonia, which doesn't have a hydroxide in it, and so it will now take ammonia, add the water. The ammonia will take the hydrogen from the water, making making ammonium, and having OH as one of the other products. Okay, so ammonia then takes the proton from water. That gives us the OH because it's lost the hydrogen. The water has lost the hydrogen. And then the ammonia now has an extra proton, and so we call that ammonium. Okay. If you ever tried to purchase ammonia, if you want it to be pure ammonia, it has to be a gas. Any other form of ammonia, if you're buying it in a liquid form, then it's always going to be ammonium hydroxide. Okay, so this is going to happen instantaneously. Notice the solid arrow. We just got talking about dynamic equilibriums. This is not going to be a dynamic equilibrium. You're going to form this in solution all day long. All right, now weak bases, they do not dissociate. They accept the hydrogen from the water inefficiently and are also weak electrolytes. So when we're looking at this, as I pump ammonia into water, you will smell the ammonia gas coming out because it doesn't want to stay like this. And that's because it wants to go back into that equilibrium. All right, but if you have ammonia concentration, then all of that ammonia concentration is going to be NH4 plus OH minus as a compound. Okay, so the equilibrium for a weak base, an ammonia molecule collides with the water molecule, and again, this time instead of the water keeping an extra proton, it's getting rid of one of its protons, and so we end up with the ammonium ion and the hydroxide. And again, it's going back and forth, and so we get ammonia and water as a product of the net reaction, which is how we get that dynamic equilibrium. Okay, so again, if you're going to purchase ammonia, it's going to have to be as a gas, or else it's going to be undergoing this process. So general ionization equations, strong acid and water. So we have HX plus water is going to give us H3O plus X minus. Strong base, and notice the arrows here, both of them are pointing directly to the product. So we get M with OH to the N is going to give me the charge of the metal. So it's M to the N plus that same number of hydroxides. Now, if it's a weak acid or a weak base, you'll notice we have those dynamic equilibrium arrows, right? All right, so write the ionization equation for each of the following with water. So I'm going to take a weak base, methylamine, CH3 and H2, and I want to write that with water. So I'm going to take water, add it to the CH3 and H2. We know that we're being told methylamine is a weak base, which means it's either going to accept a proton or donate a proton. And hopefully you said it's going to accept a proton. And so here we can see CH3 is now NH3 with it and a plus charge. And it's going to produce that OH minus. All right, how about a weak acid, nitrous acid, HNO2. Now remember the strong 7 is nitric acid, and this is nitrous acid. Okay, so completely different. Okay, hopefully since you're told it's a weak acid, you remembered you're going to have that dynamic equilibrium. We're told that it's an acid, which means it's going to donate the proton. So water is now going to accept it and make the hydronium ion. All right, number 3, strong acid, chloric acid, HClO3. So strong acid means it's going to completely dissociate, which means we're going to have a single-headed arrow. It's an acid again, so it's going to be donating the proton. And so that means water is going to accept the proton and make H3O+. Last but not least, strong base, strontium hydroxide. Now, since it's a base, we know it's going to donate which means it's going to be Sr2+. We don't need water for this one because it already has the hydroxide. Okay. All right, so brief summary then. Strong acids and bases are strong electrolytes. So strong electrolytes, that means we're going to completely ionize. All right, so forward reaction is going to dominate. So there's not going to be any return reaction, no reverse reaction, which means it's mostly products. Concentrations will be easy to calculate. Strong acids and strong bases are strong electrolytes. Again, little reverse reaction, and we'll write those equations with a single-headed arrow. Weak acids and bases are weak electrolytes. That means a weak electrolyte, you have a small percentage of ionization, and the reverse reaction will dominate. That means you have mostly reactants. Weak acids and bases are weak electrolytes, which means you have a lot of the reverse reaction, and we're going to write that equation as a double-headed arrow. All right, next up is going to be polyprotic acids. So monoprotic acids are what we've been doing with. They only furnish us one H+. So if I take that strong nitric acid and I add water, I get one hydronium ion. If I take one weak acid, I add water, I get one weak hydronium. If it's a diprotic acid, now I'm going to have two H pluses for every one acid. So for instance, sulfurous acid, H2SO3, has two hydrogens on it. So first it's going to supply one hydronium. Then the HSO3 minus can supply a second hydrogen to give me a second hydronium. So polyprotic just means we're going to furnish more than one H+. Okay? So polyprotic acids then, we could have triprotic. So if I take that H3PO4, even though it's not a strong acid, it can give me 3 hydrogens, which means it can produce 3 hydroniums. The stepwise reactions, H3PO4 plus water, gives me the 1 hydronium and delivers an H2PO4. The H2PO4 can then lose another hydrogen, furnishing another H3O+. Then finally, the HPO4 can give us that last hydrogen. We'll now have the phosphate by itself, and of course, 3 hydroniums. So the net would be H3PO4 plus the 3 waters will give us 3 hydroniums plus that phosphate. All right, so go ahead, you give it a shot. Write the stepwise ionization for citric acid. Right, this is the acid found in your citrus fruits. H3C6H5OH in water. Now I want to pay attention to the detail here. We have 2 sets of hydrogens. One of them gives us 3 and one of us gives 5. Whenever we have acids, the hydrogen out front is always what we call the acidic proton. That's a D, acidic proton. Okay, so in this case, these 3 hydrogens are acidic. That means they can come off and give us H+. These 5 hydrogens, notice how they're buried inside the reaction. They are not acidic. Okay, they're not acidic. They do not come off. They're molecular. So they're going to be connected to this molecule until we break the molecule completely apart and smash it into other ions, which is a whole different thing, organic chemistry or even analytical chemistry for that part. We will not be experiencing that here. All right, so the first step then, we're going to pop that first hydrogen off. We're going to make H3O+, and then the citric acid is going to have only H2 left with now a negative charge. We can do that again. We'll take H2C6H5O7, mix more water, pull another hydronium off, and have only a monoprotic at that point, and then finally we'll take that one off. All right, So acidic anhydrides. These are nonmetal oxides. They act as acids. So react with water to form molecular acids that contain hydrogen. So for instance, SO3 plus H2O gives me H2SO4. Okay, so sulfur trioxide, we mix that with water, we get sulfuric acid. If you take something like N2O5, again, a nitrous gas, we mix it with water and we'll get 2 nitric acids from that. We take carbon dioxide, mix it with water, and we're going to get carbonic acid. Now, ionic oxides are basic anhydrides, so they're going to be soluble metal oxides, which means we're going to start with a metal oxide and we're going to undergo an ionization, a hydrolysis reaction, to form the hydroxide ion. Sounds like some crazy terms for a simple idea. So I'm going to take calcium oxide. When I mix it with water, I'm going to form calcium hydroxide. Okay, so we're going to take a metal oxide. We're going to mix it with water. That's hydrolysis. It's going to form the metal hydroxide. The metal hydroxide can then dissociate in water. So we have calcium hydroxide, then gives us calcium ion and 2 hydroxides. All right, so more practice. Which of the following is not a strong base? So if you remember, what are your strong bases? We know that group 1A is guaranteed to be a strong base. We know 2A is guaranteed to be a strong base. So we have a 1A metal, strong base. No metals, potential there. Group 1A metal, oxide though, but it can turn into cesium hydroxide, which can then turn into a strong base. Barium hydroxide, group 2A, and again, another calcium oxide, group 2A metal, which means B should be our not strong base or our weak base. Okay, which of the following is an acid? Now I've thrown a lot of stuff at you. Which one's going to form the acid? So NaO2 we know is a strong base, right? It's got that 1A metal. All right, so no metals here, no metals here. 2A metal, strong, 2A metal, strong, right? What's up with this A, B, C, A, B? I'm not sure what's going on there. Is it going to be B or C? Now, hopefully remember, we're looking for an acid. We need somebody that's going to donate a proton. Tricky here because there's no protons in B, but that is going to be our acid, right? And hopefully you remember why. When I take SO2 and I mix it with water, it's going to give me H2SO3, sulfurous acid. All right, which of the following is a base? And hopefully you picked A, right? And the reason why we're going to pick A is we have that nitrogen there, and it's going to be very much like ammonia. So remember, ammonia was NH3. And the detail of what was happening with that, the reason why it becomes a base is it has this lone pair of electrons. Now remember, a base can accept a proton, which would be H+. So that's where that happens, is this two interact. So it really doesn't matter for the nitrogen what's down here. So we can actually turn these into R's, because R's can be anything. And so the R's down here are taking up those bonding electrons, but it leaves that lone pair up here on the nitrogen, and that's what's going to be acting as our base. It's going to be accepting that proton. If I go through here, we already saw if we add water to this, we know that's going to be an acid, right? And if we have this right here, whenever we see that hydrogen on the outside here, this is going to be our organic acid series. Okay, so we have that hydrocarbon, couple of oxygens, right? That's going to be an acid. HF, hydrofluoric acid, we know that's an acid. And HNO2, we know because it starts with a proton, again, it's also an acid. So that means it had to be that nitrogen with the 3 methyl groups on it there. It's going to act just like ammonia. All right, so we've gotten into acids and bases. Got a long segment here, but we're almost finished. I'm going to finish this segment up with naming. So acid-base nomenclature. We do have a system for naming our acids and bases. For acids, We have what's called the binary acid system. So we're going to be looking at the anion, but we also have an oxoacid system. So when you see the oxygens in there, there's a way to name those. And then finally, we have an acid-salt system. In fact, I'm thinking maybe we do a few naming sets to go through. So actually, we'll break this segment up and we'll make a second, well, I guess it'll be a fourth segment from the acid naming, because that could get a little bit intense. And this way you can take a break before we get into it. And then in that same segment, we'll get into naming bases, because there's a couple methods there for naming bases as well. So we'll stop here on this segment, and then we'll pick up in segment 4 with naming acids.